that's way off. Maybe this is it. Lost it. Okay. I'm going to get there. First of all, what is my screen resolution? Let's just go ahead and use this one. I may actually be able to solve this. Now, okay. Sorry for the delay, but now I can do so. Okay, let me make sure there's audio. Okay, I think we're audioed on. Okay, I think we're audioed on. All right, we are. Okay, so let's look at this problem. Now that I finally have this thing set, I can actually use this again. Okay, so we start with this tank here, which is obviously a triangle, and it contains kerosene, and determine the magnitude and the location of the resulting force acting along the triangular end of the plate. Let's see if this will, yeah, this works. Thank goodness. Okay, so first of all, he's pulled out the plate here, and you have a centroid that, if it's a triangle and it's 4 foot, give me a second, the centroid location is the 4 foot divided by 3, which is not 2 feet, but the center of the force, or the center of what he calls the pressure, is at 2 feet. Now let's figure out this in detail. Since it's triangular, you have to use the load, or the equations gamma h bar a for the force, and the distance, which I'll call delta, the distance below the centroid, is going to be I bar xx y bar area. Now let's review the difference between h bar and y bar. You look over here, this is the top of the water or liquid, and you have some sort of gate, the line in which they meet forms a coordinate system in which y comes here, but h comes here. Usually they'll give you this angle, and so it's pretty easy to figure out. Here, let me erase that. And I'll erase this. And I'll go back and say, let's say your centroid is right here. Then this means this is y bar. But it also means this is h bar. Now if you look at the triangle over here on the side, but you'll see something really simple, h and y. So the sine of theta is equal to h over y, or he's written it more in the book like this, which this is the case. So h and y are related through this angle. Likewise, you can look at h bar, that's one specific location, but the triangular plate is located perfectly vertical. So here's your triangular plate. from the side view, from someone standing here, looking that way, they see this. You take the line and you cross it. You take a perpendicular. This is y. And guess what? This is h. So in fact, h and y are the same thing here. If theta is equal to 90, and it is, then h is equal to y. So in this particular case, h is equal to y. Now, let me get rid of all this other mess. And one of the things we're going to have to do is we're going to have to find IXX of a triangle. Now, instead of looking down, what I'm going to do is I'm going to, I am in, okay, this is not a touch screen, so I have to do that. Just do that. Somebody is going to, and usually a lot of people criticize Wikipedia, but I kind of find them to be okay. Let me see if I can find a triangle. Here's you a triangle. Now, here's your problem with this particular triangle, and that is he has put, the coordinate system's right here. Here he put the coordinate system right here. This one is with respect to an axis through the centroid. So b h to the third over 36. So I go back to my example. I believe I can erase this. And b h to the third over 36. So the base in this case is 2 of those, or 2. H is 4 over 36. I'm looking for, what is that? Oh, it's gone, whatever it is. Okay, so not a touch screen, so 2 times 4 to the third over 36, 3.555, okay. So 3.555. This will be interesting whether if I cut that down, does it stay there? Yeah. Now, if you're wanting to know, first of all, let's find the force. Gamma, kerosene. I have no idea what kerosene is. I hate to say this, but I'm going to roll down and just pick up that piece of information. And I'm picking it up right here, 50.88. Okay, I'll go back up here. I'm just going to say 50. H bar, which is 4/3, area, which is, if that's 1 off here, it's got to be another 1 off here, and this is 4. So it's 2 times 4. 2 times 4. 2 times 4 times a half gets you back 4. So the area of this thing is just 4. So we're going to check ourselves out and see if we've got the right. I'm trying to get to MATLAB. 50 times 4 times 4 divided by 3, 266 2/3. Okay. So I get 266 2/3. I'm going to cheat a little bit, roll down, see if I got that. So first of all, we got this one. So where's his force? 2. He's got 271. I sort of dropped some of my digits, so yeah, you know, that's close enough. Now, I'm going to go in here and find the distance. Okay. The distance below the centroid of the location. Okay. 3.5556. Y bar was 4/3, and the area of this triangle is 4. So if you go in here, you'll find that its location is 3. Let's say times 3 divided by 16 gives you 2/3 or 0.66. Should be 2/3. Okay. So at this point, okay, so here's this load, which I've got a little bit different because I threw away some of my digits here. If I wanted to keep those digits, probably get that, but here, I'm going to go ahead and just to make sure. Okay, it was 0.88. So it was 50.88. 88 gives you, again, 50.88 gets you 271. So that's what you get right here. So in fact, had I carried my digits like he did, I would have got the 271. So I finally figured out how to get this thing to working. So what I'm doing is I'm covering that example. So I already streamed part of it. So what I'm doing is I'm just finish this up, and then I'm going to go work up one of the problems. But I haven't assigned those problems yet, so I'm just going to work a problem in the back of the book.
I had some problems like with some of my units for the first.
Oh, okay.
Like I never got credit for them.
Oh,
I
really?
can't tell if it was number-wise, unit-wise.
Oh, okay.
And spent some time on it.
Okay, well, I'll look at it here in a second.
But
Here, let me see. I can't roll this thing forward. Well, I pretty much completed this one. So let's look at those. And I finally figured out how to get this crazy thing to work. You do control panel. Oh, now I'm stuck. Okay, wait a minute. Let's see. Where's my control panel? See, part of it's, okay, somehow it's associated with one of the, okay, this is really weird. Okay, go back here. It remembers that. It remembers that on that screen. Now, does it remember this on this screen? It does. Okay, this is really weird. Okay, so then I can delete all that, or maybe I can select it all. No. Wait a minute. Okay. Select all? No, you can't do that. You have to go in and use your thing and delete it or erase it. Okay, but at least I got the pen to line up so I can actually use this thing again. It took me like 20 minutes or so to figure that out. Okay, so let's go to that content. Okay, now chapter 1. So which one was it, or which ones?
so on. So for problem 18.
18. That's the last one, right?
Last one. I got 0 points out of it, even though I found the right answer.
Oh, really?
Yeah.
Okay, let's try this. There you go. That is weird. Okay, so full credits granted on that one. There you go. Now, you'll probably have to wait like a few minutes for the grades to update.
Okay.
But
And like, I didn't also understand how it wound up being 16 times larger.
Okay, so why don't we?
Get rid of this A and B, or, I mean, I really didn't understand it.
Okay, let's see what his question is. Let's see. Okay, determine the torque. What is the torque? What is the torque? And he obviously goes through and figures out the torque. Okay, where was the question of the? Is the question near the end of this?
It doesn't have the answer to that question.
Oh, okay, so.
In the video.
Okay, let me go see if I can find. Okay, I'm stuck here. Okay, let me go back to it. 18. Oh, okay. If the radius of disk were doubled, the torque required to maintain the same angular velocity would be.
In like,
Okay.
If it said it, it never plainly said it.
Oh, okay.
To draw the conclusion, and I didn't get it.
Okay, so let me go to try to find. See, I don't know what disk A and B are, so let's see if I can find them. I guess I'll have to find them in the video.
Yeah, that's where it winds up being.
Okay, so there's A and B. Okay.
So if A and B, and they have the same length of 100 millimeters, let's say.
Okay.
For the radii. Yeah.
Okay. So, yeah, so let's see. So if these things are doubled, okay. Now that would be given, oh, what is he saying? He says the rotating constant speed determine the torque required to sustain the motion. Okay, then he gives you the gap. And so that would be assuming that, let me look back at, okay, where was that? It's not here.
It's another window, I believe.
Oh, is it another window? Oh, okay. Here. Oh, okay. If the radii of disk in which the torque required to maintain the same angular velocity, the torque required. Okay, so, all right, so if you think about it, he'll roll along and then you'll have the area stuck down in there. Let's see if we can roll till we find the area stuck down there. Well, I guess you have to let loose of it. There you go. And he's got his little DR, so he's obviously going to integrate along that DR. And then there's his little DF. So he's got to put that in there eventually. Okay, so wait a minute. He went down to here, and his D area is 2 pi. Okay, hang on. He must say a lot of stuff there. Oops. Okay, TR squared. So, okay, if I go in here, all right, so let me go past this integral one more thing. He should have that thing. Okay. That's maybe what I should do is bump it. So the thickness, I mean, the T is going to remain the same. That's what I gathered from what he was saying. So he's So eventually he's going to come out. Okay, that's fine. That's fine. Okay, and he's got to have one more. Okay, wait a minute. Got to have one more. Okay, so here you go. Here's the torque. He's integrating this with dr. So he's filled all that junk in, but he's got an R and another R. So if you integrate it, you should end up with an R4 eventually. I don't know where. There you go. So there's his R4. So if you double it, okay, let's see if I can hit this button. So is that it? Can I write? Can I write on this? Yeah. So if you double it, all you're doing is so let's say, yeah, if you're doubling it, you're 2 to the 4th power. Isn't that 16? So it picks it up. So if your R was, I'm just making stuff up. So if your R was 1, and this time you doubled it, you would get an R2. The first time through, it would just be R, or 1 to the 4th power. This time it'd be 2 to the 4th power, which is 16 times bigger than that one.
Okay. I'm completely missed that.
Yeah, it's, some of these things are, you know,
I mean, I knew it was there, I knew I missed it.
yeah.
Because I went through them, and then, I mean, you double it, you would assume that it would be twice as hard, like, without the.
Yeah, and I think the thing that catches you on this one as opposed to the other, if I can go back here, let's see, where was it? Maybe right there? Maybe right there. Oh, yeah. So if you think about it, the fact that this one sits, oops, wrong button. The fact that this one sits out here, the torque is actually the R times that force. I don't know which way he drew the force. He may have drawn the force.
He drew it that way.
Did he?
The bottom way.
Oh, he did? Okay. So the thing is if you're up here close, you don't find much, not contribution to the torque. When you get way out here, man, it contributes a lot. So I think that's what he was trying to do, just trying to get you, these problems I think are just trying to get you to think about it. Where were the unit ones you were? Because actually, had a percent dynamics send me a thing and said, isn't the unit supposed to be this? And I looked at it real close and I'm like, yeah, he's right. So they sort of messed up in one of the problems in dynamics. So given that, there is a possibility that that's the case. So yeah, if you find something like that, let me know. And then let me just go, let's see. What that is? Well, that's average score.
Units. There was like one of them with like.
Was it one of the ones with hints?
Probably.
Just go to,
Yeah.
there's the rain cloud one. That one probably.
Oh yeah, that's why I'm remembering the unit problem. I put the answer for part C and part B.
Oh.
I put it wanted mu, and I put u instead of mu.
Oh,
So like it didn't, the variable was wrong because I didn't know how to put the Greek letter in there. That's what it was.
oh, okay.
I think I understood the problem. It just was a pain in the there here.
Oh, okay. So this is the way you generally see them. See them like this. Ooh, okay. That was that. Okay, wait a minute. Okay.
We still plan on having that quiz Friday?
Yeah, I'm just going to pick a problem off of the thing and drop it on there. It's being held, but I think I'm going to drop some of the problems and pick one of the ones we've already done. So this time I think I'm going to run from Thursday night at midnight, and I think I may run into Sunday at midnight for this one, just to get us all through the first one, you know. So I don't think I'm going to do a Friday class per se, lecture-wise, and then that way you can, you know, go mess with it a little bit. So
It'll be on Blackboard though, right?
yeah, well, you'll go to Blackboard, then you'll burrow into this system through the Blackboard. Some people are burrowing in. Apparently, you can go around Blackboard and go straight to this.
I did that the first time.
Did you?
I was doing the access code.
Oh,
Because I
okay.
didn't know you could go through Blackboard. I wished through the access code, so I've done it both ways.
Oh, okay.
Whichever way is easier.
Yeah, I think that.
Whichever way I remember.
Yeah, as I say, I think that the fact that you got a Blackboard means that most people are going through the Blackboard because it's right there. I've got to the point where I'd only do that. So it's pretty much the same. So you got comments view. What is that?
But like one of my things, I kept trying to put like meters in for the unit,
Uh-huh.
and it wanted it in meters, and it would not take it for some reason.
Really?
I don't remember what it was, but I would put the M in, and I made it capital, I made it lowercase, I mean, I did whatever it wanted, and it just would not work.
Hmm.
And I can't remember which one it was for the life of me. I think I got credit for it, so like.
Well, then that
It's not the
probably.
end of the day, but I was confused by it.
Well, there's also, let's see, what is it? Express your answer in three significant. The viscosity of that's it. Determine the kinematic viscosity. And express your in three significant. But does he have? Okay, so he's got vector. This. I don't see the units.
It's already wrote down on the side.
Oh, there it is. Okay.
Yeah, like sometimes it requires a unit, sometimes it don't.
Oh, okay.
And then you gotta figure out what it's wanting and make sure you do it right.
Okay. Can you make this else in? Yeah, I see what you're saying. It's stuck right there.
But like sometimes it's not. Like sometimes it's like there's a question where it wants value and
like right
units. And terminus shifter, yeah.
Okay, so when you do units, I'm assuming, okay, put in a fraction. So you're wanting to, let's just try this, meters, and I guess you just go, okay, second, but then when you do that, okay, wait a minute, can I do this? Second, and then do I hit right and do,
You went subscript on
oh, that's weird. I thought I wanted to go, I guess what he wants, okay, he wants first, second, And then he wants that. Oh, okay. Here, I don't even know what here, let's just put in a number 5 and see what happens.
Yeah. But like, it doesn't tell you whether your units were off, your value's off.
Oh, but it says enter your answer in a different unit type. Review a list of acceptable units. Oh.
You can go through and find units or whatever, but like.
Oh, cool.
So let's go to distance, area, and volume.
Distance, area, and volume. Okay.
So like, one of them was wanting it in meters.
Oh, so
and
this
I would
is.
put M in, and it wouldn't take it. I don't know what else to do. Like, I had capital M, I had lowercase m. It just would not take it at all.
Oh, okay. So he's wanting it, if it's meters squared, he's want that little caret symbol is what he wants. Enter that. Okay.
So, I guess I just need to fiddle with it more.
Yeah. Yeah, and I haven't, let's see, I bounced out of that, but how did I, okay, so here's the problem. I just made stuff up. So my question is, does he want, wait, let me go back to the list acceptable units. Let's find pressure. Pressure. How do you enter? Enter pounds per square inches, pounds with a divide by sign. Okay. Pounds per, this is PSI. Okay. All right. Or you can enter PSI.
Like, sometimes you can enter a unit and it doesn't count off for it. And then other times it does count off for it.
Oh.
Like, sometimes you enter a unit, it's like, we don't understand this unit, try again. And then also, if you put in the wrong unit, it's like, no, you're wrong. And you can't tell whether it's just a unit or the number.
Oh.
So that's where it becomes a pain in my derriere.
Well, and this is, I can see, okay, so if you look at this, we're multiple terms like Newton meter per radian. Choose A over B, not the divider, and then enter Newton meter and go down and then enter radian.
Yeah.
So it's, that can be, but if you have, now see, this is annoying because actually a programmer would not like that because it would the programmer would say precedence operates kilogram divided by meters. You stop there, figure that out, and multiply it times seconds. So to me, I would see that as being kilogram second meter over meter, not what he's got. So in these divide by things like that, they all should be in fractions, in my opinion.
And then you put parentheses around them if they're not in
Right.
fractions. But anyway, I mean, potato, potato. I
Yeah.
guess they're all the same thing until they're not.
Exactly. Okay.
Anyway.
All right. Well, it's a good system in many ways. There's little
Like,
bits
and I'm
of
not just trying to sit here and complain about it. I'm
Yeah.
just trying to figure out how to
yeah.
get it done.
That's what that once you figure out what he wants, you know, that'll be majority of the issue.
And then also, like, another thing that I'm curious, so let's say I do first attempt at problem sets. And
Uh-huh.
like, I get them wrong, but like at the end of the day, I figure out which one's right. I don't get credit counted to. If I go back to them, will it be the same problems or will it be different problems?
That I don't know. I'm not sure.
Because if it's different problems,
Then you got to rework.
then I gotta rework everything. It's
Yeah.
not just the fact of like, you figured it out once, way to go.
Yeah.
Is the numbers gonna change? Is that all, or is it the actual
Yeah.
problem gonna be different? Like in a different ways, you ask for a different portion of it?
Yeah, that's a good question. I don't know the answer to that.
Okay. I guess
So,
I'll have to figure it out.
Yeah. You know what I could do is put a couple of single problems out there and let people fiddle with them and just get credit for them, and they could just fiddle around. I put too many on the first assignment, and I did that on purpose to get us all like engrossed, and then I'm gonna start trimming it down a little bit. So,
That's
so,
fine. I mean, I'm just asking while I got time to
yeah,
ask.
yeah, and I honestly, I'm trying to learn it myself, and, you know, they supply me on the supplier side. Sometimes I don't see what's happening on the other side, you know.
Okay.
So, all right. So you know what I'll do on Wednesday? I will, hang on, let's see. I'll come in here, go back to, and I'm gonna go here. I'll go to the book. Let's see, I was in the book a minute ago, but I don't know where I was. Maybe it'll remember for me. I was at that triangle. There, okay. And then if I go up here and hit this, okay, so there's a problem. Understand a plane surface geometrical method. Okay, looking for the problems. Examples: stability, buoyancy, fundamental problems, and then problems. I think the fundamental problems have videos with them, but I might be wrong. Looks like I'm wrong. So what I'll do next time is I'll just roll through and do a bunch of these, and then I'll go back in and just do a few problems themselves. There's not much different. I mean, he has nice graphics and everything. I want to do a couple manometers, and then I'll want to do a square gate, a round gate, or a triangular gate, maybe a round. And then, so that one looks good. I mean, just looking at the pictures, you can kind of tell which ones look good. So I think I'll do that one. That one looks okay. Rectangular. And then I've got to get into, okay, so those are still rectangular. I'm looking for one that is a circle. There's a triangle, there's a circle. So I'll do this one. 276. So 74, 75, and 76. So the problem is he's got two things. Use the formula to tape rho is equal to fish will determine the resultant force. Exerts on plate A, so that's the square plate. Okay, if the tank is filled with fish, will determine the resultant force. Exerts on plate B, that's the circle, and the location from the bottom of the tank using the formula. So I'll do this one and this one. Hey, I'll highlight it.
Alright, there, you can find it. They say hunt for the pink one.
And then, I don't know, let's see. I'll do some curved gates. That one looks fine. Okay, 91, 92. We'll do that one. However, I may just do both of them because they both have, they're both talking about the same picture. He does an excellent job with his pictures. Oh, and this is a tricky one because actually I'll do that one because that's very tricky. And then we would definitely want to do a curved one. And we definitely want to do an inverted curved one. So I got a bunch to do. I don't think I can get all this done next time, but I'll focus on the ones that'll be in the homework for this coming Sunday first. So I'll need to sit and pick the ones and then go back and do those. To drain the shank from a four-sided pyramid when the tank is completely. Determine the resultant force acting on each side and its location measured from the top of A. That looks intriguing. It's a triangle. It gives you all the dimensions.
Pyramid?
Yeah, in other words, the sides are all kind of triangles, so that's kind of a triangle there. Let's see if this works on that. Yeah, so this would be a triangle. And then it's 6 foot out. I'm sorry, 6 foot tall, but it's 2 foot tilted back. So from the side view, it kind of looks like that, although it looks like a straight line, not a. So it comes down 6 and back 2, leans back 2. So what you got is the whatever liquid is pushing on it like that. So actually, if I was going to be like perfectly, it would push like so on it. So that would be a good one. It stays there. So I'll do that one. Let's see. Trapezoid, or a tapered thing. So what I'm going to do for the Sunday one is make sure we know manometers and just flat gates. So I'll work on those, Mark, first. And then next week we'll do the curved gates and then the strange shaped gates.
That'll be in the next week's homework.
Yeah.
Okay.
Chapter 2 is a strangely difficult chapter.
Pretty lengthy and like just a lot to cover.
Yeah. When you get into 3, oh, it jumped. Okay. 3 is kind of, it's a good one, but it's not as, I don't know why I've lost. Okay, here we go. So he talks about general fluid flow and the way things flow. So it's not as big of a deal. But this chapter 4 and 5 are where things kind of start really happening. So you get control volumes, and again he jumped again. So he talks about control volumes, and then he gets into the working energy. Let's see. So he talks about Euler's equation, which isn't as big of a deal, but then it should break down eventually to. It's kind of interesting. He calls it this because this kind of breaks down shortly to Bernoulli's equation, which maybe. Okay, I got to the end of that. That's the example. Okay. There we go. Okay, well, wait a minute. That's the energy equation. Bernoulli's equation. There it is. So I went too far back and then too far forward. So that sort of breaks down to that, which is super important. And there's things that we talk about there that we solve all sorts of stuff. Then he goes to applications of Bernoulli's equation, which is probably some things we've seen before, like airplanes and flow from, this is flow from reservoir. He does a pretty good job, I think, with it. Then, and he gets, okay, so he does that one where you can actually use the Venturi meter here to get the flow rate down the pipe. Just because you have to have 2 different diameters, and you tap off of those two, and you get the delta P, and you can actually back out the flow rate through the pipe without actually ever putting a meter in there. And it works well, it's very reliable. And then energy and grade lines, and that's moderately important. Actually, if you get into any sort of civil engineering, that's really important. It has the standard thing, which we have the energy line, hydraulic grade line, and then a datum. And then thing I don't do a lot of is I don't do a lot with the energy equation, because if you get in here, because Bernoulli's equation is a form of the energy equation. The reason I don't is because that's a lot, that is thermo. And so I basically say, let's keep that reserved for thermo. And some people, here. And that's pretty much it. Then you go down to fluid momentum. Then we do linear momentum, which that's interesting, because you can figure out what type of forces are put on there by fluid flowing. Now I got to cover 7 very deep, and then cover 8, and then okay, so he does enclosed conduits and pipe flow. Okay, so he has them separated. Very interesting. So most books put those together. 9 and 10 go together into one chapter. So I don't know. I hate to say let's go, but I may cut off the stream because